you see on the bottle this. What is the difference between CO and CO? One stands for cobalt. Right. Okay. One of them stands for cobalt, CO. This is a metal. It's located there in the periodic table. Of course, you can find and so forth, right? You look here, it's number 28. No, it's number 27. Okay. That is just a natural element. Okay. But capital C, capital O means carbon bonded to what? Oxygen. So this is carbon monoxide, right? Like if you hear some joker that puts the car in the garage, leaves it running. No, I'm serious. Tries to kill herself or whatnot. Well, carbon monoxide. It loves to bind to hemoglobin. It does so much more readily than oxygen, and it basically suffocates you. Totally different chemistry than cobalt. What's the only difference? The capitalization. So see, these are the type of reasons why I really stress this. I mean, let's look at fluorine for an example. The abbreviation for fluorine is F, okay, not FL. And people have gotten into me with that, and they're like, well, golly, Dr. King, obviously I'm not talking about the state of Florida. I said, yeah, I know that, but you could be talking about fluorine bound to a coordinated ligand. They're like, well, we've not even learned about coordinated ligands. I was like, yeah, I know that. Okay? But in 5 years you might. In pharmacy school you might. So you can't go ahead and look at the bottle with capital L, FL on it. That's a total different scenario than F. All right? So that's the first thing. If it's a single letter, it's always capitalized. Second thing, if there are 2 letters, the second one is always lowercase. Never the other way around. Okay? Like, you know, if you had Ni, if such a thing exists, which you very likely could inside of a high vacuum environment or so forth, this would be nitrogen bonded to iodine. Okay? Now, this right here is nickel. So see, just because something like this, right, you know, I was a gas-phase chemist when I got my PhD. So you could make something like this. No problem. They couldn't keep it around the bottle. I mean, you could make something like this, and they've got totally different chemistries. Now, if it's got 3 letters, what does that mean? Well, that is the Latin word here. Okay, so like UQ stands for una quadrum. That's Latin for 114. Okay, so that means they have not been named yet. So how do things get their name? Well, the International Union of Pure and Applied Chemistry, which is like an organization that has scientists from all different countries and so forth in it, gets together and they decide on the name. Okay, now some of these are kind of neat, like for example, where do you think berkelium was found at? In Berkeley, right? Over in California. Same way, what do you think americium was named after? America. All right. So a lot of these, Neptunium, of course, Neptune, Californium, after, of course, California. I mean, you know, so a lot of these things, they get together and they say, okay, what are we going to name these things? Something like Seaborgium was named after a scientist that did a lot of work in radioactivity, Seaborg, and so forth and so on. So that's the first thing. Okay, what else about this periodic table? Well, this periodic table has things going up and down, okay, and they also have things going across. Now, the going up and down are called what? What's it called when it goes up and down? Well, that's true. That's absolutely right. That's called a column, all right. But in chemistry, we call that a group, all right. Now, the way it's done now generally, the International UPOC, they number these things in columns from number 1 all the way through number 18, all right. And chemists a lot of times denote themselves by the group that they study. For an example, I am a group 16 chemist. I suppose if you want to know my specialty, group 16, which means that I study the oxygen, sulfur, selenium, tellurium, not so much for polonium because, well, so that's what I study. All right. Now, the old-timey way, which also has benefits, is like in your textbook in the very front cover of your book. You will notice that this is called 1A, 2A, and then they skip some, and this is called 3A, 4A, 5A, 6A, 7A, and 8A. Those things in chapter 10 are what are called your valence electrons. In other words, those tend to be the electrons that drive the chemistry within the group. All right? So, group 7A, what that means is there's 7 electrons there, and most of the time those 7 electrons are what participate in the bonding. All right? Now certainly you can go into core electrons under extreme circumstances, but we're talking about generally. Okay, now why is that important? Because everything underneath each other tend to react similarly. I did not say they have the same reactivity. They tend to have similar reactivity. And one of the classic examples that I can give you, and we can go into lab and do this if you want, is you can take a lithium, which is a metal, and drop that in water, and what you will have is you will have like a fizzing, something like a small little piece of Alka-Seltzer or whatnot, not too glamorous, aside from the fact that a metal would actually disappear kind of right there in front of you. Now, if you took sodium and placed that into water, what would happen is a small fire would start. So then you would have this metal burning on top of your water. It's kind of spectacular. And then when you went down and had potassium and put that into water, there would be a pretty good substantial fire erupt, kind of immediate-like, and maybe it would even throw a small little sliver across the room. Okay? And as you go, and that's all we've got here. And as you go down to rubidium, you put that into water, you have an actual small explosion on your hands. And then as you get cesium, when you put that in water, you have quite the explosion. All right, like reach out and touch you back there in the back row type explosion. All right. What am I trying to tell you? Well, I'm trying to tell you that just because they're underneath each other there, they tend to have the same reactivity. Think of it like from a biology perspective, if anyone's ever heard of the sodium-potassium pump. Well, take a look at that. They're right underneath each other. They can tend to go back and forth readily. I did not tell you sodium and potassium reacted the same. I said they have similar reactivity, similar electronic structure and the such. All right. So that being said, let's just look at the periodic table here. Who's ever heard of ATP, adenosine triphosphate? Okay, what's that for? Energy, right? They call that the powerhouse of the cell inside the mitochondria, and it's got this Krebs cycle generating and glycolysis and electron transport and all that. Adenosine triphosphate, ATP. Phosphorus, okay? Now what would happen if you started eating arsenic? Would that hurt you or not hurt you? Well, that's going to hurt you. Think about it. Because your body initially says, wait a minute, when you're eating arsenic, your body's saying, I'm eating phosphorus, this is good. So it starts putting it in its place, but guess what? No cigar. So what do you think arsenic's going to do? Well, it's going to start shutting down some of these processes that are based on phosphorus. And when you start tinkering around with Krebs cycle, electron transport chain, and all this, then you got trouble. Okay? So again, look underneath these periodic tables, right? These things are like this for a reason. Now, let's just say that you are a chemist, and sometimes when you're a chemist you have to go see the doctor, like every 3 months, 6 months, whatever you're working with, and they examine you. So if you go into your occupational position and you're a strontium chemist, what type of things could start happening? Look at where it's at in the periodic table. And I know this is early on to be asking these type of questions, but what type of things could start happening? The calcium's above it, right? So what could happen is whenever, okay, first off, and this is a periodic law, which is not in chapter 3, but we'll get to it later. You guys know what a bond is? I mean, generally, we have a whole chapter on a bond, but basically it's how two things stick together. Totally introductory, right? Okay, well here's what starts to happen. As you go down in a periodic table, the bond strength typically gets weaker. So if you had a calcium and a phosphorus